Hello guys, welcome back to my channel Gamma Di Gamma. So in this video I would like to cover some complex analysis from the scratch, because I think this is a really important topic, especially the viewers of this video, the viewers of my channel. They have seen me use contour integration quite a lot again and again. I think I should give like a small derivation or like an intuition behind it. So let's get started. Okay, so before we move on to anything else, let's first discuss what a complex function looks like, or what it is basically. So consider a complex function w that takes an argument that belongs to the complex plane, spits out something that belongs to a complex plane. So such a function, let's say w of z is the input, looks like some small function u of x and y plus I times small function v of x and y, and u and v are both functions that take inputs in the real space, spit out something in the real space, so they're real functions, and x and y are some real inputs. And it's also worth noting that z is equal to x plus iy. That's the general representation of a complex number. Okay, let's look at some examples of this actually. So assuming you have w of z is equal to z cubed, we know z by this definition is x plus iy cubed. Well, if you just expand out everything, you have x cubed minus I y cubed plus I 3x squared y minus 3x y squared. Group the real terms together, so we have x cubed minus 3x y squared plus I times 3x squared y minus y cubed. And you see w of z is precisely of the form that we predicted it would be, because in this case u of x and y is this first, the real part, x cubed minus 3xy squared, and indeed it's a function of x and y. V of xy is indeed the second part, the imaginary part, 3x squared y minus y cubed, and indeed it is again a function of x and y. So you see how this works, and you can just extrapolate for other functions. Okay, so now let's move our discussion to the derivatives of complex functions. So you have wz and you differentiate that with respect to the only parameter it has, z. Well, you can write the principal definition of the derivative, the limit definition. I'm sure you know this from Calc 1. And you can further split this up into so you can basically use the split the w into its respective functions u and v. So u of, well, it's x and y, so we'll have to take two limits, delta x and delta y. You say x plus delta x and y plus delta y minus u of xy. You can divide this by, say, delta x plus I delta y, and probably have the imaginary terms. So we'll have to just, I think, add. Probably we can add here, maybe same limit. So I probably can bracket this v of x plus delta x, y plus delta y is v of xy, same denominator again, delta x plus I delta y. Okay, so I mean, you can probably extend a derivative like this. Now there is one issue, however, because notice that u and v are like multivariable functions. So there's a problem when it comes to multivariable functions, because derivative can be taken in multiple directions, because it's the direction of approach. I mean, in single variable calculus there was this direction of approach and or this direction of approach, right? There was the left hand derivative and the right hand derivative. In multivariable calculus, however, there's like multiple directions of approach, and each of them might give different answers for a derivative. If you recall, in single variable calculus, if the left hand derivative did not match with the right hand derivative, then the derivative did not exist. So in the multivariable calculus scenario, it wouldn't make sense that different directions have different derivatives. We need to have a unique derivative irrespective of the direction of approach in order for the derivative to exist. So we need to put some conditions on these expansions that we've obtained, and let's do that on a fresh page. Okay, so this is the expansion we got, and I'd just like to point out that z was x plus iy. So if you use the properties of a derivative, you get delta z is equal to delta x plus I delta y, and that's why we got the denominator this way. The rest is just the definition of w, because w can be broken down into real functions u and v with this I in them. Now if we evaluate limit as delta y goes to 0 first, well, all these delta y terms will go to 0. So this will go to 0, this will go to 0, same thing here, this will go to 0, and this will go to 0. So finally we have limit as delta x goes to 0, u of x plus delta x at y, comma y, minus u of xy over delta x plus I times v of x plus delta x, comma y, minus v of xy over delta x. Of course, this is bracketed out. And now notice the first term is just the partial derivative of u with respect to x evaluated at xy. I'm calling it a partial derivative because u is a multivariable function of x and y, plus similar thing here, I times partial derivative of v with respect to x at xy. And that's pretty much what you get when you use the delta y inside, or you evaluate the delta y limit first. Now what if we evaluated the delta x limit first, and we can interchange limits, because I mean the functions are continuous. This is certainly a valid assumption, because talking about differentiability doesn't make any sense without continuity being in place. So this is sort of legal, I guess, if you want to talk about that way. And when I do that, I hope you see that now the delta x terms will go to 0. So this will go to 0, this will go to 0, this will go to 0, this will go to 0 now. So I have limit as delta y goes to 0, u of x comma y plus delta y minus u of xy over I delta y plus I times v of x comma y plus delta y minus v of xy over I delta y, bracket it out, I is gone, you have negative I, and now notice the first term is just the partial derivative of u with respect to y evaluated at xy plus, now I is cancelled out, here it was 1 over I, which is negative I, partial derivative of v with respect to y evaluated at xy. Now in order for the derivative to be unique, both these things should match because they originate from the same definition of a derivative, this which remains the same. I mean, this general structure remains the same irrespective of the direction, because the direction comes in this like limit part of it. So in order for the derivative to be unique or independent of direction of approach, this guy should be equal to this guy. So now if you compare real and imaginary parts, you're going to notice that partial derivative of u at xy with respect to x is going to equal the real part, which is this derivative of v at xy with respect to y. And this is the first observation. The second observation is if you compare the imaginary parts, the derivative of u with respect to y at xy is going to equal the negative derivative of v at xy with respect to y. Sorry, with respect to x this time. And these conditions, or these rather equations, if you want to put it that way, what do you call the Cauchy Riemann equations, or you can say conditions if you want. And if this is true about a function w of z, which can be expressed as u of xy plus I times v of xy, if a function, a complex function, can be expressed in like this, and if that function satisfies these criteria, then it is uniquely differentiable. On any arbitrary point z0 that belongs to the complex plane. Or let's say a neighborhood of z0, because derivatives are all about the neighborhood and locality. And this term of uniquely differentiable on a neighborhood, you call such functions which have this property holomorphic functions. So instead of saying this big thing, you can just call them holomorphic functions. So Cauchy Riemann equations, if any function like this satisfies these equations, then it is holomorphic. That's the basic idea about this. Now finally, I would like to draw a parallel. So assuming you know some basic vector calculus. So if you have some vector function which takes an input x, probably, I don't know, which can be expressed as this column matrix of a, so the first component will be some simpler function of x and y. Second component would be another simpler function of x and y. Sort of like similar to what we had with the w. A simpler function like u plus I times another function of v. I mean, this I tells us that it's another dimension, or it's another component, it's a fresh component. Okay, so assuming you take the curl of v, you're gonna get assume your curl is 0, then you're gonna get partial p with respect to y minus partial q with respect to x is 0, which means that partial p with respect to y is equal to partial q with respect to x, and then assume that the divergence of v is 0, which means that partial p with respect to x plus partial q with respect to y is going to be 0, which implies that partial p with respect to x is just negative partial q with respect to y. And if you compare this and this to the Cauchy Riemann equations, you see like a similarity. What curl says is that there is no rotation in the vector field. Like if you like sketch out each vector in this vector field, there's going to be no rotation, no net rotation. And the divergence 0 says that there's no sinks or sources. I mean, there's no like random stuff coming in or going out of anywhere, and it sort of makes sense. I mean, you can sort of draw parallels between these two conditions of no rotation, no sinking, no sinks, no sources with Cauchy Riemann equations, because they sort of guarantee like a uniform layout of the land where there's no like unexpected stuff. Rotation is something that's unexpected in like a vector field. If you look at it from like a calculus point of view, even like sources and sinks, they're like these infinite these points where stuff like blows up or like just blows down from a quantitative perspective. So Cauchy Riemann equations, they sort of guarantee like a uniformness, like a stability. I'm gonna quote it because this is not a right description mathematically, but I hope you get the point here. Now, one final point I would like to make with respect to complex functions is that our regular real functions, the sine of x, it is directly extended onto the complex plane. You just input a complex value z, and the rest just takes care of itself, because you can just use the Taylor series and it'll basically be the same. Because I'm going to talk about more detailed stuff in probably like a video on the Laurent series maybe, and then you might understand the distinction, why such functions can directly be extended and why others can't. Like even like the cosine, it can directly be extended. Just plug in the complex value. Exponentials, definitely. I mean, those are like very important. But natural logs, for example, now when you extend it out, you'll have to use the polar representation, r times e to the I theta, which becomes natural log of r plus r times I times theta, and you'll also have to look at something that's called the Cauchy principal value when you're determining what angle to choose for theta, because theta can be 0, it can be 2 pi, 4 pi, even multiples of pi, odd multiples of pi, like half integral multiples of pi, whatever. I mean, so you need to choose like we chose one, like we chose like inverse sine of 1 is going to be pi over 2. Like we chose pi over 2, we could have chosen anything else. Same way we're choosing in this process of Cauchy principal value. So I hope you get the idea, and many of like rules apply. Many of the rules that apply to real functions apply to complex functions, like chain rule of differentiation, all the rules of differentiation, indefinite integration, and stuff like that. And we'll explore more in the future. So stay tuned. Peace out.